My name is Elimboto Yohana from Dar es Salaam University College of Education, which is a consultant college of the University of Dar es Salaam in Tanzania. I'd like to thank all the organizers for giving me an opportunity to present to this conference. And my talk is about recovering 21 centimeter signal from simulated fast intensity maps. FAST is a shorthand for 500-meter aperture spherical radio telescope, which is the largest single-dish radio telescope in the world and possibly the most sensitive single dish within its frequency band. In our study with FAST, we have prioritized the use of H1 intensity mapping for a number of reasons, as you can see on this slide. But most importantly, H1 intensity mapping sacrifices on resolution and inserted focuses on aggregating or collecting neutral hydrogen signal distribution information over large patches of universe volume. The underlying neutral hydrogen signal distribution will enable us to constrain cosmological parameters such as dark energy equation of state at low rate shift through matter power spectra. In our study with FAST, we have used a number of parameters, as you can see on this slide, and they will make reference of some of these parameters as we move on. Neutral hydrogen signal power spectra is particularly very important and of our interest, and this is the average neutral hydrogen signal power spectrum computed at the mid-frequency of the frequency band of our interest, which is 1255 megahertz. As a number of colleagues have already pointed out, the biggest challenge of using intensity mapping technique is the foreground contaminants from our Milky galaxies and the extragalactic point sources. Known contaminants include galactic synchrotron, emission, which is the most bright foreground caused by emitted electrons spiraling in galactic magnetic field. We also have emission from the background of extragalactic point sources, thermal noise, free radio emission, RF 1RF noise, time variable noise, and atmospheric effects. This is a simulation of various sky components in terms of power spectra, just to show their magnitude. Most importantly, 1RF noise is of particular interest, and as a power spectra density or PSD for thermal and 1RF noise contaminated receiver is given by this question here, and the limit for which the spectral index of the frequency correlation is defined, that's the value of beta, has the following interpretation. When beta equals to 1, this means noise is uncorrelated in frequency, and for beta equals to 0, means noise is correlated in frequency. This is a simulation of 1RF noise, a projection in equatorial plane as a Mollweide view. 1RF noise has features that look more or less the same as the neutral hydrogen signal of our interest. Our interest is to apply PCA, which is a simple and parametric method for extracting useful information from a high-dimensional data set. This is a blind approach. So PCA reduces a high-dimensional data set, in our case N mu by NP, where N mu is the number of frequency channels and NP is the number of pixels of temperature fluctuation map, by projecting it into a smaller dimensional subspace. Compressed data set usually captures the essence of the original data. We have an advantage that, as many colleagues have already pointed out, that the foreground is expected to be smooth and correlated in frequency. This property enables the PCA to cluster the contaminants of foreground information and strip it off the sky. This is a simulation of the frequency spectrum for galactic synchrotron, the galactic point sources, and the free emission. Actually, is the temperature flux at a given pixel, and the higher temperature at lower frequencies expected due to the galactic foreground signal domination. Applying PCA to clean the maps and ultimately end up with the power spectra is equivalent to remove the first few principal components, equivalent to the principal axes 1, 2, and 3, and the features that correspond to these principal components or the sky information is almost 99% of the whole sky. So PCA result, as we apply one mode, remove, you can see that contaminants are suppressed, but we then attain almost perfect remove of contaminant after applying 4 modes, after removing 4 modes by using PCA. We also check how the input and output neutral signal maps compare to each other, and find that the standard dispersion between input and output signal give us the value equals to 0.034 millikelvin, indicating that PCA is robust and can systematically reconstruct the neutral hydrogen signal. We also represent our result in terms of power spectra, and from the upper left panel, this is the power spectra simulations without thermal noise after removing 1, 2, 3, and 4 modes. And also on the right panel, that's top right panel, the simulation includes thermal noise, and for the lower panel, we include thermal noise, but because the PCA is hampered by systematics and noises that make it difficult to completely recover the noise, and these systematics and noises add some bias to PCA, and we try to debias the recovery of nitrogen signal by taking the foreground map plus noise plus nitrogen signal, apply PCA, and then subtract the foreground map and the noise map after applying PCA as well. So after doing that, we almost recover the nitrogen power spectra perfectly. We also performed the Fourier transform on the data cubes with the given information. The data cubes were of 10 degree by 10 degree, and with a range of right ascension from -5 degree to 5 degree, the declination of 150 degree to 160 degree. For frequency, range from 1050 megahertz to 1250 megahertz. So they computed two-dimensional power spectra, look of the recovered and the simulated signal are very close to each other, indicating that PCA can do well in recovering the signal, but with some small mismatches. We assumed the spatial flat lambda CDM model. So this is the result of transforming the data cubes and then computing the power spectra, two-dimensional power spectra. So as you can see here, there is the simulated neutral signal and the recovered signal are close to each other with some small mismatches, and the difference or the level at which PCA is able to recover the signal can be seen by comparing the recovered signal and signal that's contaminated with the foreground. We also checked how the precision of PCA, that's the neutral identity signal recovery, varies with observational time. And I find that if we increase the observational time, PCA recovery precision is likely to increase. Similarly, if we decrease the survey area. Thank you for listening.